Okay, so I don't have a section that I teach of this material, but I thought I'd splice together a couple of hints and thoughts and a few worked out examples that might make this more interesting. Now, this particular section is just simply titled Problem Solving, Guidelines and Hints, which is a fancy way of saying we're going to throw stuff at you and just see how you do. But there are some suggestions. So one of the goals that the college is saying we want you to apply is to use this 4-step problem-solving process and then to use appropriate tools to help make the job go easier. So the intention is to have access to a calculator and a spreadsheet, and the intent that you're going to solve some sort of application problem. Alright, so what is this 4-step problem-solving process? And they are pretty straightforward. Number 1, understand the problem. Number 2, devise a strategy for solving it. 3, carry out your strategy, and if it doesn't work, go back and try again. And step 4, look back and make sure that your answer actually makes sense. Now, underneath each of those steps, there's some more sort of hints and suggestions about that. So, for example, under understanding the problem, and actually, before I go through this, one of the textbooks I teach out of actually gives one of the best math advice ever. It says if you're doing an application problem, step 1, read the problem. Step 2, reread the problem. And step 3, go ahead and read it a third time. And it just emphasizes that students just get in a rush and don't really take a chance to actually understand what the thing is asking them to do. So if you read a question and you can't rephrase it in your own words, you didn't read the question carefully. There's either a term or a vocab word or something in the problem that just went right over your head. So you want to go back and reread it enough that you can actually explain to a complete stranger to the problem what's going on in the context of this. So underneath this particular step, understanding the problem, they say think about the context to gain it, so make sure you can put it in your own words. Is there a way that you could make a list or table? Are there actual numbers that you can play with? Can you draw a picture? Can you think of a mental model or a written model that might describe the solution? And all those are good steps. Under step 2, to devise a strategy. So once you've got an idea as to what it's asking, you come up with a plan. What do I see the general idea is with these numbers, or what kind of pattern can I see with the numbers? And then go ahead and carry the pattern out and see if you can see a bigger idea going on. Anyways, so this is the part where I go, yeah, they're just throw some math at you and see what you do. Step 3, follow through on your strategy. Now you think you got a plan, go ahead and do it. And if it doesn't work, so if you try a couple of steps in your pattern and you recognize it's not working, abandon ship and go try again, which is kind of hard. Some students, and I actually find this a little unfair for math. Think about, and if you happen to like math, then that's great, but if you don't, think about what you do like. Maybe it's cooking, maybe it's dance, maybe it's music, maybe it's sports. And let me ask you a question about this. So think in mind of your favorite activity outside of math. You got that image in your mind? Okay. Let me ask you a question. Are you perfect at it every time you try? Let's say your favorite activity is dance. Do you just pick up the dance the first time you try it? Or do you make mistakes? Right? Now here's the question. If you make mistakes, I assume, because sometimes in math people make one mistake and they just give up because they assume they're terrible at it. But if you're really excited about dance, when you make a mistake in the dance, do you just stop and give up and say, well, I guess I'm just destined not to be a dancer? Or do you get up and try again? Right? As a matter of fact, if you really think about it, if you really enjoy dance, don't you make tons of mistakes, but you just let it roll off your shoulder and you don't really care about it? Well, in math, I see a lot of students that just get frustrated because they didn't get the answer right the first or second time. And yet, the things that they really enjoy, they'll tolerate errors and mistakes tons of times. But math, they only tolerate it once or twice. And yet, they will claim that they are really talented at that thing that they like and not so talented at math. And I'll go ahead and share a secret with you here. I like math. I enjoy it. But I probably made more mistakes than anyone that's watching this video will ever make. The problem is, or not the problem, but the thing for me is, when I make a mistake in math, I don't let it affect me. I don't let it stop me. I keep going. So this step 3, I think, is a huge step. I think a lot of students see that their approach is not working, and instead of revising, they just say, well, I guess I'm just not talented, and give up. And that's sort of the idea, that you constantly reevaluate your strategy and try again. And then step 4 is to take your answer, and does it actually work? Does it make sense in context of the actual question that you originally asked with? So we're going to look at some examples. Okay, so first off, notice that I went ahead and opened up Excel, and I put a practice problem in Excel. We will get really comfortable with Excel this semester. So if you're not familiar with it, I definitely think it's worth just playing around with and trying some things. And as I like to say, get messy and make mistakes. So let's jump into this question, and then we'll kind of talk about some strategies on how to answer it. I'm going to read it to you out loud, and you're more than welcome to mute me and then read it to yourself if you need to. But it goes like this. Tickets for a fundraising event were priced at $10 for children, $20 for adults. Shauna worked the first shift at the box office, selling a total of $130 worth of tickets. However, she did not keep a careful count of how many tickets she sold for children and adults. How many of each type did she sell? Now, going into this, I'm going to rephrase some information. I know that kids cost $10 and adults cost $20, and I know she sold a total of 130. What I don't know is I don't know how many total tickets she sold, so that kind of makes it a little bit of a and it asked me for how many of each type could she have sold. Okay. Well, let's start with this question. Is it possible, so I'm going to come over here, and I'm going to do like this. So I'm going to say children in one cell and adult in another. And then I'm just going to start with this idea. Is it possible that she could have sold 0 children tickets and would be able to make the 130 off adult tickets? In other words, do I know for a fact she sold at least 1 kid ticket? And the answer is I do, because adults are $20, and there's, you know, she sold 10. Well, if she sold 10 adult tickets, that would be $200. So it's got to be 5. If she sold a 5, then it'd be 100. But it's got to be a multiple of 20. It can't just be can't just sell half an adult, which would be a child. So in other words, I can't start with 0, but I can start with 1. And so if she sold 1 adult, and we'll kind of think about this for a second. Now in Excel, if I'd like to use it, if I just hit equals, then I can type in 130 minus 1 times the 10. Now I know we could have done this in our head and got 120. So I know she spent $120, and then from here I can take the 120 and divide that by 20, which means she could have sold 6. Okay. So that's an answer. However, are we done? Is that the only correct answer that she could have gone with? Well, let's up some numbers and see if that makes sense. Could she get away with selling 2 kids tickets and then an unknown amount of adult? Well, here let's watch me make a mistake, and well, it's not really a mistake, but it's not going to work out. Because if she sold, let's see, 130 minus 2 times 10 puts it at 110, and if I take 110 and divide that by the 20, I don't get a whole number. Okay, so there's no way she could have gotten away with 2 kids tickets, but could she have gotten 3? Well, let me do that math again. So 130 minus 3 times 10 is 100, and 100 divided by 20 is 5. Okay, so she could have gotten away with selling 3 kids and 5 adults. Now already we kind of stop and go, 1 and 3 worked, but 2 didn't. And so what do 1 and 3 have in common that 2 doesn't? Oh, 1 and 3 are odd numbers. So already I'm beginning to suspect that, well, maybe odd numbers will work for children and not even numbers. So to test that, I'm going to try 4, and I'm going to claim that 4 does not work. So if I do 130 minus 4 times 10, I get an odd number, and I can't take that number. So this isn't going to work. I get I need an even number, a whole number out of this. So 4 does not work, which we guessed out of our pattern. So that means 5 should. So 130 times 5, 130 minus 5 times 10 is 80, and 80 divided by 20 is 4. Okay, now, so we know that works, and then we notice, hopefully we notice another pattern. So on the left we have odd numbers, on the right we have even, not even, we have just start at 6 and count down. So with that said, then we can, I suspect then that this should be 7, and what would this be? This should be 3. And so we'll test that real quick and double check our pattern is a real pattern and not a fake pattern. So 130 minus 7 times 10, and 60 divided by 20, and in fact it works. Okay, so I think I've got a hold of this pattern. So the next number here would be 9, and this would be 2, and then 11, and that would be 1, and 13 and 0. Now you're probably thinking, wait a second, is that even a possible answer? Well, what's 13 times 10? 130. So it's possible, but I suspect she probably would have been aware of this. Shauna probably can remember if no kids at all showed up, or I'm sorry, no adults showed up and it was all kids. I don't think she'd be that ditzy to get that confused. But it is a possible numerical answer. So there's our list of possible correct answers for this particular problem. Okay, so here's another example. We'll read it and then we'll talk through what it's asking and then think of a strategy. Jack and Jill run a 100-meter race. Jill won by 5 meters. Well, good job, Jill. So Jill was clearly faster. And that is, Jack could only run 95 when Jill crossed the finish line. So Jill ran 100 and Jack only was able to run 95. They decided to race again, but this time Jill starts 5 meters behind the starting line. Assuming both runners run at the same pace, who will win? Okay, so we have 2 races that happen. The first time Jack and Jill are put at the same starting point, and Jill manages to go the whole 100 meters, whereas Jack only goes 95. So then they decide they're going to rerun the race again, and I guess it's kind of fun to think, you know, well, how if Jill is that much faster than Jack, and since he only beat her by she only beat him by 5 meters, what if we put her 5 meters back and we assume they run? We're ignoring the fact that in real life I would not run, I would just be sitting there, but that's not the point. So we're kind of curious, can we get them to cross at the same time? But what are we assuming is true in both cases? We're assuming that they run the same pace. Well, what does pace mean? You gotta think for a second. Pace is a speed, right? Well, where have we seen speed in the real world? Cars, driving cars. So miles per hour, meters per second, that sort of thing. So what if we calculate their actual speed and see if we can determine how fast they're actually going? Okay, now in figuring out, so let me kind of write this down here. So we got Jill and we got Jack, and I'm going to make this a little bit bigger so that people can see that a little bit easier. Okay. Well, let's make an assumption. We don't know how long it took them to run the race, but we know that we know how fast they ran. So let's assume that it took 20 seconds for the whole race to happen. And I just made up a number, right? But I'll show you kind of what happens, regardless of the number that I choose. So Jill ran 105 meters divided by, and I'm going to click on, actually I'm not, hold on. Hold that thought for just a second. Bear with me. I need to get rid of that. It needed to be a number, not a word, but that's okay. I'll just put seconds next to it. Okay, so Jill ran 100 divided by, and I'm going to click on this number. Okay, which means if it took her 20 seconds, then she was able to run it in 5 meters per second, right? Jack, on the other hand, he only ran 95 in that same time frame. So I'm going to click on that. And so in that case, he ran 4.75 meters per second would be his speed. Okay. So then we're going to go to race 2. Race 2. And in race 2, Jill is able to, she's still running at that 5 meters per second, but she had to run 105 meters because remember she started 5 meters back. So I'm going to take that 105 and multiply it by the 5. I'm sorry. Okay, I'm sorry, I misspoke. I want 105 divided by, so I want to take the distance divided by the speed. Oh, I'm making all sorts of mistakes here. Okay, so equals, this is how Excel knows we've got a formula. So 105 divided by that number there. What that says is she was able to complete the race in 21 seconds. Okay, then for Jack's time, he only had to run, this time she started 5 meters back, so he ran 100 meters this time. And I wanted to, well, I'm all sorts of wrong here, divide that 4.75, and so he was able to complete the race in 21.1 seconds. Okay, so Mark said go. Who wins the race? Jack does. Okay, but we got to be a little careful with this because Excel is a little tricky. In that, I wish I hadn't shown you this. Sorry, not shown you this, but I'm going to tell Excel to give me more decimal accuracy on these particular answers. Okay, you know what I said about making mistakes? I just said one myself. Okay, so think a little bit carefully about how long it took. So when the gun went off and they started, Jill finished the race in 21 seconds. Jack finished it in 21.05 seconds. Who wins? Jill wins. Right? Jill won that race. Okay? And you're probably thinking, hey, Brother Soleil, wait a second. We made an assumption. We assumed that it was 20 seconds to win the first race. But notice, if you followed what I did with Excel when I clicked on these little boxes, if I come up here and I change this to say 10 seconds, notice all of these other times also change with it because I linked all these cells together. So if I make my initial assumption was 10, then Jill wins the race in 10.5 seconds, Jack wins it in 10.53. Who wins? Jill does. And I can come up here and I can tweak all these numbers all I want. And the magic of Excel is it'll always kind of change all the other numbers that I connected. But any assumption I make about how long it took them on the first race doesn't matter. Jill always finishes a little bit ahead of Jack. Okay. So, answer is, assuming both runners will win, who's going to win? Jill will, always. A little bit quicker than Jack will. Okay, so this is another one that, well, let's read it, and then we'll have the oh my moment. Two cars 120 miles apart begin driving toward each other on a long straight highway. One car travels 20 miles per hour, and the other one travels 40 per hour. At the same time, a canary sitting in one car flies back and forth between the two cars as they approach each other. As the canary flies 150 miles per hour and turns around instantly at each car, how far has it flown when the cars meet? Alright, you ready? Take a deep breath. Oh my. What? Okay, so we have these two cars that are going towards each other. You can kind of see them here facing towards each other. And we have this bird that starts at one car, goes to the other one, turns around and goes to the other one, turns around and goes to the other one. So he's going to go back and forth tons of time. And what I want to know is when the two cars meet, I hope that doesn't mean crash, but when they meet, how far has this bird gone? Okay, so kind of get that look of horror in your face. What I want to do is I'm going to make sort of a makeshift number line, and I'm going to, because you know there's only 120 miles total, so it can't take them too long to meet up, right? So I'm going to start at 0 and then 10 and then 20, and then the nice thing about Excel is I'm going to tell Excel, hey, I'm going to hit equals. Would you go to this previous number and just add 10 to it? And Excel goes, okay. But the nice thing is I can drag this along and it will do that. It'll go to the previous cell and add 10. And I'm going to go all the way till I hit 120. And when I hit 120, I'm going to stop. Okay. And what I want to do then is I want to call this car A, and I'm going to call this car B. And car A, just so we're all aware, is going, we're going to let him be the 40 miles per hour, and car B, we're going to let him be the 20 miles per hour. Okay, so what's going to happen? Well, hopefully this works out nice and pretty. Actually, the way the numbers are, it is going to work out nice and pretty for us. So before you go, but wait, what if it's not an even number? Relax, okay? Just relax. All right, so if car A starts at 0 and he goes 40 miles per hour, then at the end of the first hour, where is he? He must be at 40. Okay. What about car B? If car B goes at 20 miles per hour, he must be, at the end of the first hour, he must be at B, right? Okay. Then we're going to go back to car A. We're now at hour 2, so from the first to the second hour. And if car A is at starts at 40, we go another 40, he must be at 80. And if car B starts out at 100, he's got to go 20 miles per hour. So after an hour, he's not at 100 anymore, but he's at 80 again, right? So here A and B both meet up at the 80 mile mark. More importantly, how long did it take to do that? It only took him 2 hours. So this bird is going to go back and forth for 2 hours. Some of you are probably thinking, wait a second. So if he's traveling at 150 miles per hour times 2, that means he must have total traveled 300 miles. And that's a lot easier than any of the oh my's that you probably would have had. So I mapped out a number line, sort of figured out how long the bird was in flight, and then took advantage of the fact that he's moving at this constant speed of 150 to get the 300. All right, let's do a sock question. I've got 3 blue and 3 red socks in a drawer. Without looking, how many socks do I need to pull out to guarantee a pair of red socks? Okay, so here's the catch. Half are red, half are blue. I need to make sure that even though I'm not looking, I don't know why you would pick your socks out this way. I don't know, I got a drawer full of white and dark socks, and my wife's sleeping, so sometimes I've done this game. It's lots of fun. So without looking, how many socks do I need to pull out to guarantee that I get a pair of red? Okay, so I've seen students get frustrated and go, I don't know, how do you know how many? Well, let's assume we are just the worst puller in the world, and whatever I want I don't get. Okay, so what could that be? Well, if I am looking for a pair of red, the first time I pull out a blue, and then I reach back in and I pull out a blue, and I reach back in and I pull out a blue. That's pretty much worst case scenario, right? First 3 things I pull out are all blue, 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 right? Well, at that point, when I reach back in a 4th time, what am I guaranteed to get? I'm guaranteed to get a red. And then what am I guaranteed to get after that? Another red. At that point I stop. I've got a pair of red socks, right? So worst case scenario, how many total socks did I have to pull out of this bunch to guarantee that I ended up with a pair of red? I pulled out 5. Whoops, 5. That's what I meant to write. Then we're going to go to the second question. Second question says, without looking, how many socks do I need to pull out to guarantee a pair of red or blue? Alright, so we kind of open up this or. You're thinking, oh gosh, last time it was 5. So I know at most it's 5, but I have sort of opened up this red or blue bit. So again, let's go at this assuming we are just the most unlucky puller and see what happens. So I'll reach in, I'm going to grab something. It's going to be a blue, right? Now, again, I'm assuming the worst case scenario. So when I reach in, I'm going to get what I don't want. I've already got a blue, so if I was to pull out another blue, I could stop at this point. But I'm not that lucky because I'm going to pull out a red. Okay, so I got one blue and one red so far in my hand. And I'm going to reach in, and this time I got to think. Does it matter what I pull out? If I pull out a blue, I've got a pair. If I pull out a red, I've got a pair. So at this point, it doesn't really matter what I do. I'm going to pull out a pair of something, be it red or blue. So in this case, the answer is 3. If I don't care what I pull out, as long as it's a pair, then worst case, 3 choices.